as well. Yeah, perfect.
Okay.
Working?
Yeah. Sorry.
Okay, thanks.
And share the screen, right? I think I didn't share.
Yeah,
Sorry.
Can you make the phone with you?
How to use?
Oh, can you make this host?
Yeah. Please
So
make
we
us
can-
host.
So we can
host.
share. There we are. Okay, thanks. So this is a session that came out pretty spontaneously, sort of a week ago. To say the idea is to say something about this cloud native geospatial thing. And since Leandro talked already most of the hour about cloud optimized geotips, we will now talk about cloud native vector data. And so there's GeoParquet and GeoArrow. Try to explain a little bit for those less involved in what this means, what this means. I actually prepared a little thing that worked, but that's on my computer. My computer is there, and I'm now on Leandro's computer, so I get away with that. But Leandro has things that work, and that he will show afterwards. But if you want to see what I tried, then here is a Docker link to a Docker file. This is my OGH22 course material page, where I added this link to a Docker file that when you build that image, installs GLGeos Proj from source, installs R and installs Arrow and Parquet stuff, and then builds the whole thing. So you could actually run it because you need relatively fresh versions of everything. Zoom in, yeah, I can zoom in. Thank you. There's nothing to see yet, but it's basically a long, install of everything. Here there's source installs from Proj, Geos, GDAL, and then comes the whole stuff from. This is already the spatial packages, and here is the whole Arrow, the whole sort of Arrow stuff. There's a lot of things, and for some reason I couldn't get him to get this thing to build on my Ubuntu 20, which is still 24. But anyway, everyone else can, so I'm not complaining. So where is my other? Where is the tabs? Oh, there. Hi. Good. So what's columnar storage? So what are tables? Yeah. First of all, we're talking about table data, basically table data such as CSV files and tables you find in relational databases in simple sort of two-dimensional Excel spreadsheets, our data frames, pandas, and so on. Have the following properties. Basically, we have a row-column layout where we think records as being rows and typically corresponding to observations if we have data, or to items or subject or something like that. And variables, we have variables in columns, and they are of a homogeneous type. So they are variables that reflect to a certain variable, right? A certain property, right? That is of a single type. That could be like a number, like an age or something, a floating point number, a date, or a text like a name, etc. So variables typically have names, and records usually don't have to have names. Sometimes they do. Spatial data in tables is usually stored by adding a special column, as we've seen in my lecture yesterday and in Martin's lecture this morning. We have a geometry column that basically does stores all these numbers in a systematic way, such that we can figure out whether it concerns points, line strings, polygons, and so on. Consider this little CSV file, which I typed here. Yeah. So this is basically a CSV file as text, as you see it, as we read it, and that means that the files, as you know, hopefully are a sequence of bytes, right? And that the sequence of bytes really goes as in text. It's a text file, so it goes in reading order. So it starts here with this quote, and then comes the V, and then comes the rest of this line. Then comes a new line, and then comes the first character of the next line, and so on. So it is really sort of, that is the sort of the reading order. That is also the order in which the data is stored in that file. And that means that basically the first line is special, is of course has the variable names. CSV file with a header. But that means that to find the first record, we have to first read the whole first line. And to find the third record, we have to we go through the first and the second line. We have to find the first new line and the second new line. And only after that, we find the start of the third record. So that means that we have a record order of the data. So it is stored in record order. So if this is a very large file, and we want to read basically one variable out of that, you can imagine that you have to read every line and find the place where is this variable. So we have like 135 variables on the line, and we want to find variable 89. We have to go to that line and then go to the count 88 commas, and then the thing we find until the next comma is that field of the variable. So that is not sort of thinking of finding variables, that is not very efficient. If you read this thing, this is an example in R, but anywhere else, it's the same thing. As I learned this morning in Pandas, for instance. If we read this thing, it looks like, and we print it, it looks again like the same way, because we think record as lines and we think variables of columns. But if we look at the data structure of this thing, this of course is a data frame, read.csv gives you a data frame, then we see that the data frame consisting of 3 observations, the 3 variables, is really a list with 3 elements. So it is a container that has 3 variables, and the 3 variables here is first a numeric variable, then a variable of type date, and then a variable of type character, right? So it's really a collection of variables that is the underlying data structure. And you can see here that if I unclass the data frame, so it no longer has a class attribute, so I ask R basically what type of vector is df, everything in every data object in R is a vector, and it says it's a list meaning the generic type, right? The list is a vector of anything. So this is a list, a container of columns, and I can see that by basically making it a list again, so that removing the data frame property and by removing the class attribute of the data frame. So it is now a list, and we see, the list has 3 items. It has this variable, this var A, it has this date variable, there's a name variable, and then it still has an attribute called row name. So apparently read.csv added row names to this. So this is what we call columnar storage, right? So we have these variables, and the variables are vectors. And the object that we have is a collection of columns. It's not a collection of rows. So that is the way things are stored in data frames are stored in R. And that means that values in a column are stored continuously in memory. And instead of storing record 2 directly after record 1, basically the value 2 of var A is stored directly after 1 and before 3, right? We have the value 2 here in memory in the sequence. Numbers 1, 2, and 3 are sort of in continuous memory. We can, of course, we can hack this. We can fake some kind of record, some kind of row-wise structure. For instance, with this function, when I say rowify this thing, where I basically say, well, create a list from every row of this data set. So I take the first row, I put it in the first list element, put a second row, put it in the list element, put a third row, put it in the list element. So then I have a list of 3 records. This is, of course, outrageous and complete nonsense to do, but it would work. You can experiment and you can see, for instance, what happens if I have a somewhat larger, it's still quite small, 100,000 row data set with a variable with random numbers. Here a character variable, and here date values and so on. So you could sort of look at how long does it take to compute the mean of what I'm going to do. The mean of the first variable, the random numbers here. When I rowify this thing, or when I do this directly on the column, right? And you can see here's a little benchmark. This first function basically is a for loop, where I say I take df.rows, so that is the rowified data frame. So that's 100,000 records with just rows, with row data frames, single row data records in it. And I loop in in a for loop over this, I learned from Christoph how to do benchmarks in a readable way. And here I do a for loop and then sum by hand basically the values and divide them by the length of the array. The other way, what you could do is using an asset which is an alternative for a for loop, and use a double bracket, and that you would think that it's faster. Well, it's not. This is basically cruciatingly slow. It takes half a second. This is even slower. It takes more than half a second, and this takes microseconds. So it's a different unit. So milli to micro. So it's a factor 1,000, like 3,000 faster. Right? So that's the difference. 100,000 rows going through it and putting it together and so on, or just having this thing in constant memory. And you also see that the memory overhead is much smaller from doing that. Yeah, so that is obvious, and that is of course the reason why RWorks and Pandas worked with columnar data structure. Of course, another reason is that that R can't deal with heterogeneous records really well, and so it doesn't have a concept of a record or a struct or something like that, like C or C++. So yeah, so you can do that. So this is just an R. So we have in our data frame our column stores, and we see now a lot of other systems that basically also do that for obvious reasons. That this is faster. An open source database that is now used a lot by people who say, well, if I have a problem, I should parallelize, but where Spark is too much, then it seems that DuckDB is the thing to go to put your data, and that has Columnar Storage. Google Bigquery is another thing, and Google Bigquery is one of these data. This is one, and SAP HANA is of course a commercial one, but not, for instance, regular databases, right? One of the reasons that these databases do this is that very large databases are really hard to manage. So if you have if you have a Postgres database of several terabytes or something like that, you want to do a database dump because you need to update software or whatever, then that's going to really be hard. Another thing about relational database is that they run. Yeah, so the database runs and waits for something to do, right? So it's active. It's a running process, and quite often you don't want to have something running, because something that runs needs to be kept running. Running is expensive, and running in clouds is often more expensive than storage. Yeah, so you would really sort of like to pay for your computing, but not for keeping something waiting or something active or so. So the whole idea behind Google Bigquery is, for instance, that it's what they call a serverless data warehouse. That it's a stateless database. It's not like running like PostgreSQL. It's not running. It's just something that you send the query to. It starts up. It reads the data. It does the query and it kills itself. Yeah, it outputs whatever you want it to do and it stops. So in that sense, it's stateless. It's not kept running. So what you pay for is the storage of the data and the compute cost of starting up, reading, processing, and stopping. Yeah, so that's everything that is then what's being paid for. And if you work with clouds and big data and so on, then this is one of the costs that you would like to minimize. And then, of course, comes the question: okay, if I have several terabytes, hundreds of terabytes of CSV files, what is the cost of reading that? Yeah, and then you find out that it is actually not very cheap. Yeah, that CSV file is text file. That although you can do it, Google Bigquery can do it fast, it's still a cost, and it, if you have to do it repeatedly, it can become a big cost. So there was a question: can't we do this more effective? And it can, and well, there is how can we read and write? How can that be done faster? And basically, what you would like to do is that you have a binary format, because reading binary information is always cheaper than it is always, because there's no interpretation of numbers, right? You don't have to convert the text string into a floating point number. So binary is always faster. You would like to have something that's indexed, meaning that you don't need to figure out where row 500,000 starts, but that you really know where this is. You would like to have a columnar storage model, right? So that you don't have to go through all the records, but can do these fast operational chunks of memory at once. And that means that you analyze by variable rather than by record. Of course, not for every query this is more efficient, but it seems to be efficient in many cases. So what does Parquet do? Parquet is basically a binary columnar storage. It's indexed, it's compressed, and it's chunked. Yeah, that means that it is sort of chunked means that it's not like one big file that is zipped or something like that, but it is sort of in parts. It is chunked in parts of whatever 60,000 records or something like that are written together, and then the next 60,000 come. And it's really the idea behind it is that it's meant for storage. That means that you write it once and that you read it often. It's not meant for being the fastest option to process. Arrow is something similar. Arrow is also a file format. It's binary, it's columnar, but it focuses more on memory layout and on speed of processing. So it is not the goal is then not to get the minimal storage possibility, storage size, and so on, but is really on high performance. It is even a memory layout. So arrow files can be in memory, in working memory, in which case, of course, they are even much faster to access than when they're on disk. Both Arrow and Parquet are Apache projects. That means they are both open source, cloud oriented, and there is this whole Apache project behind them. And there is also this Voltron data company spending a lot of money in their development. And they have a lot of venture capital. So there is a lot of high quality developers, so to speak, working on it. So a number of people working on the geo extensions of that. It includes Joris van den Bosse, also of GeoPandas fame, and Dewey Dillington from S2 and SF fame. And there is also GDAL drivers now in GDAL versions of 3.5 or larger, which is the latest release, that have drivers for both Arrow and Parquet. This was what I'm going to show us on my other computer in this Docker image. And they can read and write these files, yeah, just like regular like geo packages, you can read it. But there is also, in addition to that, there is a columnar read interface. Yeah, so the way GDAL, the OGR is sort of the vector part of GDAL, the way OGR reads features. It's basically you read a feature, that means you read a record, yeah, and then you go to the next record, and then you go to the next record, and so on. And you can, of course, say with an SQL query, I only want to access a couple of fields and not all the fields, but nevertheless, you have a record-wise access. So there is now an extension to the GDAL API, essentially, that allows you to read a single column of a particular file, which is then, in particular for these two data types, probably much faster. But it's something that we haven't available. We have not available yet in SF, for instance. And then you need, of course, to think how to distribute things over cores and machines and so on. So this is what I want to say, a little introduction of what columnar storage is and where this comes from, what it is. And now Leander wanted to show a couple of things, right?
So just to ask, how operational is this? I mean, this is something new, let's say, 6 months ago or something?
Well, that's a good question. So if you look at the GDAL Parquet driver text, for instance, it says, well, it works, but take into account that this is, let's say, a standard that's under development, right? So it's implemented with everything that is agreed upon now in a certain version of these Parquet and Arrow libraries, but it may change, right? It's not stabilized. It's not fixed. Like GeoPackage is pretty much fixed. They're not going to change it anymore. Yeah, but given that there's already so much effort in working software and so on, it is relatively a thing that will really
the general design idea won't change. It will just get better and better, right?
Yeah, and you may have to update at some stage to GDAL 3.6 if things change and they modify it. And so there might be some.
There are two things that are on the roadmap for GeoParquet which will change. One is the spatial index, which is currently not available. You could do it when you store the bounding box in your maximum as columns. You can use the without predicate to use kind of like R3 index on top of that, but that's not part of specification right now. And the second change, which will be larger, will be different storage of geometry. Because right now GeoParquet stores geometry WKB, no binary, but it will use by the geo-arrow specification. It will be much faster to make the predicates on the geometry. So
yeah,
it will not be necessary to decode.
Right, with more indexing information. Yeah, thanks.
So thank you, Edson. And Martin also to explain about the GeoParquet specification. So basically, what I will show here is one kind of application that we are developing inside of OpenGeoHub. So I tested really with the real data set how we can access specifically Parquet, not the GeoParquet, and I tried like directly with the exporting the GeoParquet using GeoPandas. I had actually, to be honest, I don't remember exactly what the problem that I had, but my main goal here in the beginning was actually use the this Parquet format as we are doing with the cloud optimized GeoTIFF. So I would like in the beginning to have a kind of URL with all the records, and as for example cloud optimized GeoTIFF access, we can access just a chunk of the data. My goal was actually do the same with kind of point data. So we have a kind of like really thousands of and a couple of millions of points organized in our workflow, and we were looking for a solution that could really helps with that. So in this overlay workflow that I presented in my last session. So basically, that was the goal. And I tested this write like a Parquet file using like millions of records derived from a LiDAR data. I will explain a bit more about it. But ideally, and now it's clear after listen, Martin, also Martin, right from the Julian. He's actually the maintainer of the driver for the GeoParquet in Julia. He also explained about it that there is no like implemented yet like spatial index. It means that if you have, I don't know, millions of points, you cannot retrieve them for like a bounding box. You cannot like, I just want to retrieve the points. For example, I have points from the whole Europe. I would like to retrieve just points for a specific area. So, so the way that I did it, I use it just a kind of what Parquet can offer, and I'm accessing the data, just retrieving some columns of interest. So the example that I have, it's here. I will put in the Mattermost. So in the geospatial title, and I have it running in my environment here. Okay, that's the right one. So basically, and I will clear all outputs. Okay. So yes, basically what is the application that we tested? We have this ISAT data. It's a LiDAR satellite that basically it's an active satellite that emits a kind of pulse to the Earth and receives this back as a, so it's a signal, it's an active satellite that emits like a signal and receives and interprets the signal. And basically you can use this data to derive like informations from the Earth's surface. But more than that, you can derive like vegetation structure. So you have different applications for it. And there are some like different technologies of how you can manage this this kind of data, LiDAR data. But specifically here, I'm using a kind of post-processed product that already use this kind of raw data and derive what we are calling canopy high. And it's actually the product called it like that. So you have a full documentation explaining all the technical details about it. But one thing that it's really interesting, you have this kind of relative high of not the vegetation, but for anything in the Earth's surface, right? So it depends on the vegetation, the signal can change. But they derive, so they provide, the NASA provided as HDF file format, and basically you can download it using like an automated script with curl. And we downloaded it for these areas, Brazil, Europe, US, and Mozambique, Zambia, Malawi, and Zimbabwe. And considering all these areas, I think it was more than 20,000 HDF files. And I will show the script later, but what I did, I just used it like a simple Python script to read all these files. There are like, I don't know, hundreds of columns and fields. I just retrieved the fields of my interest, like several vegetation high. We have a kind of like a full distribution of vegetation high in a 100 by 100 plot, and some additional confidence flags. But we end up, so the result that we are providing here, it's actually like just like these records, removing, for example, okay. So one thing that is important when you download, for example, a HDF file, it's a kind of ground track. So, for example, it not remove the points outside of your area of interest. It will retrieve, for example, a HDF file. If I'm like really interested in Brazil, it will retrieve a HDF file with several LiDAR footprints and LiDAR data, like outside of Brazil, but that are like saved in the same storage in the same file. So the script that I used, I just did read all these files, remove, for example, points outside of Brazil, Europe, and really stick to my region of interest. And I also removed, for example, there are some points that they couldn't calculate the vegetation height. So it's just like an invalid value. So in the end, we produced this amount of points. So it's 60 million of records for Brazil and for the other countries. So it's really a large data set. And again, the goal here, it's not I will download this file and I will work locally. No, and the goal is really access it through cloud directly to your programming environment. So in the way that I could do it, it's basically, we are doing the same approach in the hackathon, but it's basically using this S3 file system. So this is a functionality of the arrow, and it's basically, it's mapping a kind of HTTP URL for kind of file system. And again, you can easily retrieve all the columns that you have available for the data set. And here we can see that there are several columns, but the most part of the data set, it's actually this kind of canopy, I just kept the original name of the that NASA defined it, so it's easy to track with the official traits and track with the official documentation. So, so you can see, for example, we have the percentile 0, so that's the lowest canopy high. Could be more related, for example, with the floor, with the ground, and you have the highest vegetation, so percentile 100. And here we have multiple percentiles. But what is matter? This is just, again, just accessing the scheme. So I didn't retrieve any data here. I'm just like accessing the metadata, and I can see that we have these columns. And so using this columnar strategy explained by Edzer, we can actually retrieve just the columns of interest. So, and of course, ideally, and maybe it will be possible in the future with the next implementations. On top of that, we could also retrieve just like some set of points that match and that are located in a very specific region of interest. But here there is no spatial filter. So it's just like reading the data, but restricting it for the columns that you are informing here. So instead to read the whole percentiles of vegetation high, just reading the 0, the percentile 50, and the percentile 100. And even so could take a while, because now it's actually downloading the data, but it's just downloading like, I don't know, maybe 10, 15% of the data set. And this is a very, like, I didn't implement any kind of partition there, some fancy ways to really improve the Parquet format. And you can define some different strategies. And here I just use it like the standard way to save it in Pandas. I will show the script that generated it, because I would like to, my interest is actually really host like kind of one single file or a set of files on the remote place, like on the internet, as I'm doing here. So yeah, it's still reading. And one thing that I did, so it's not ideal, of course, but considering that we had 4 like very distinct regions, I just split the file in like considering these 4 regions. So of course, if I had like a spatial operator, I could put all these records in one single file and do like filtering the geometry to really retrieve just Europe or US or other region of interest. Okay, so we have the data, and unfortunately I didn't calculate the time, but it took, I don't know, took more than 2 minutes. And yes, this is the amount of records that we have. So basically, again, this is just a Parquet file, but it's a pandas. And as we have the longitude and latitude, now we can convert it to a GeoPandas and do some spatial operations. But again, this data now it's on my machine, and from here it's just like work with a kind of local data that I read. So here it's just a way to plot the different canopy height, so I can see the kind of distribution of so it's a large data here. It's considering like everything, but it's a way to plot how many. It's a histogram of how many, indicating like the distribution of vegetation height for these 3 columns that are red. And yeah, it's taking a while. And in the meanwhile, you can use it. This is the full data set, and you have the official documentation of the product here. So all I kept, for example, the same column, so you can really trace, okay, maybe some of these columns I just added later because I noticed, okay, it's important and some of them I didn't. So there is way more that I'm not considering, and so you can, for example, here you can just see how they generated it, and there's a full specification for it. So for some reason, my machine is struggling to generate the. Yeah, I still have RAM. Okay. So this is interesting. So this is the distribution of canopy height considering these 3 percentiles. So for what file we read, for US. So this is the whole ISAT points that we have available for this product. So it's huge, basically. And again, this is was just calculated considering my my machine. For you have like a confidence flag. So it's with this flag you can basically like screen some points that, for example, the most part of the points they have more than 50% of canopy and more than 50% of ground, considering the methodology. But for example, if you want, you can just remove, for example, the points where you have less than 50% of ground, because it could indicate some error. So what I will do now, so I will take advantage of this sample method, and you could try to export like a big geo package with all the points. It will take a lot of time, and so what I'm doing here is just like a sample, a random sample. So I will just select randomly. Here it's actually, yes, it's 100,000 points, and so selecting them, now I can create a geo data frame with GeoPandas. So I have the longitude, latitude, and after that, it's necessary to set the projection system. Okay, now I have way less points, but still it's 100, and it's randomly spread all over data set. So still it's valid to do some modeling. And you can use now the functionalities that we have available in GeoPandas to do a plot and see, for example, what is the distribution of points. So we can see here where we have like more and less points is basically covered the whole US. And as I mentioned, when you download the HTF files, you have a lot of points that are outside of US, because like the way that the satellite obtained the data, it's actually passing like a ground track here, and you have a lot of observations outside US. So I already removed them in the pre-processing of this data set, and now you can just save it as a geo package and work, for example, with the work in a QuantGIS. So the message here, it's actually, we have all these kind of new and native cloud formats, and so we can actually organize the data in a different way that allows, for example, really like quickly access and subset, for example, the data set according to the needs of the user. So just to download, for example, imagine to do it, you need to download. NASA is doing awesome work providing this data, but still you need to download everything, and you need to read the data. You need to remove, for example, everything that it's outside of US. And if you have it like in a format that it's really proper for cloud, you can do it like as we are doing here. And in the future, you can with the new implementation of GeoParquet, you will be we would be possible to really select for a specific area and really do like spatial queries with that. So, and just to finish, I will show the script. It's really nothing special, but it's a very basic script. Just to, it's one method that you can use to just read different sections of the HTF file. So here are all the properties that I'm reading. So it's just like a quick way to do it. So you just pass like a HTF file here, and it retrieves and reads everything, creating a data frame. And here it's a way to organize like the canopy high data. Some of this data it's actually with like invalid, not invalid, but it's like a kind of empty value, so they couldn't process it because of the lack of points or some problem in the data acquisition. So basically I'm also removing it. Yeah, I'm rounding everything for 2 decimal place. And so considering all the tracks, because with this LiDAR data, basically we have kind of 6 tracks, and there are different qualities and characteristics for each of these tracks. I don't know too much about it, but this is just a way to aggregate it. So, and here it's like an outer loop where I'm just reading all the HTF files, and in parallel, so we used a high capacity processing server just to read multiple files and aggregating them. So the way that I'm actually creating the Parquet is very basic. So after that, I just found that you could have like some partitions that allows, for example, do a kind of attribute filters, but you need to kind of design the Parquet file considering the carries that you want to do for specific columns. So I didn't test it, but it might be a solution, for example, to do some carries in a not in a spatial, but for, I don't know, give me just the points with a specific greater than some specific value for the tree height. And here also I'm using the S-join just to remove the points that are kind of outside of my region of interest. And yeah, that's all that I have to show. It's just like one demonstration that I think it was really nice, this exercise. And after that, I decided to host also the hackathon data as Parquet. But I already noticed that there are some problems with dependencies in R. And I also noticed that it's possible, but it's more tricky to set up the R arrow package to read directly to the cloud, through the cloud. So yeah, still I think there are some challenges to really solve and start using this data set, but definitely I think that's the way to go, considering the usage of vector data for this cloud native formats. And yeah, that's all. We still have time for questions and to open discussion. I know that maybe there are some people that has more experience with GeoParquet and even the Parquet format. So yeah.
Does anyone have experience? Did you ever work with it? Yes.
Yeah.
Should be fun. Large data set, also 100 million points.
Small data sets, it was just for benchmarking and figuring out how to transfer data between data science and software teams in our company, basically. So, but very promising. We store them in S3 buckets now. I have no problems with the R package.
Okay.
It just takes a long time to install because at the moment I'm not that far that I configure everything. I just install everything basically, right? There's like a full installation that you can do. It takes about 15 minutes for the package to install, but then everything works.
Great.
Because I did the minimal installation first and then saved some Parquet files from Python, but I couldn't read it in R because the compression wasn't available. And then I just did the whole thing
and it works beautiful. So,
Great.
Yeah, for me, it's really a lifesaver to have the compression in GeoParquet, because I've done this as well, but then globally. Then you have these H5 files, which are compressed, and they are okay to use if you've done these kind of extractions. But if you then think I have the world of ISAT, I think 20 terabytes at the moment, something like that. I'll just extract the coastal files, only my XYZ points that are of interest, and I save it as geo package. That should be a whole lot smaller, right? Only the coastal files, only 2 or 3 attributes. Turns out to something be 2.5 terabytes in geo package. So with GeoParquet, it turned out to be a few hundred gigabytes. So at least in factor 10, I've seen factor 20, and now it fits on my laptop. So I can actually work with the ISAT data on my laptop. So I'm really happy with GeoParquet.
Great.
And nice to see ISAT, by the way. Lovely data set.
And the only thing really that's missing to visualize that large data, right? Like cloud authoritative, to have a fully, exactly what we have for rasters, that we have for points and lines and polygons. So that's missing, because we will have to build up also kind of pyramids for points or something, right?
Yeah, there is a promising kind of format, map vector tiles, MVT, and there is a nice solution. I tested a bit this one, so it's led by the main developer of PostGIS. So, but this is it's a kind of different word. It's in a PostGIS, but basically what it does, it's a kind of pyramid structure for vector data on the database. So they have I'm just trying to find the column. There's a function here where they use to, yes, this one, yes. So basically what they do here, you can have like millions of points, not points, more polygon, but also point. And this is just, as far as I understood, creates a kind of like a coarse polygon representation. So that's why it needs to, in this case, it's running the database, because you are close to the data, so you kind of create simplified versions of the polygons with less vertices. And basically, it works nice for polygons, but for points, I did a test, didn't make so much difference, because you need to aggregate points by cluster and things like that.
I don't want to say too much, but because I will talk about this in my
Okay.
But there is, for vector data, cloud optimized visualization format that is called PM tiles. That is created through the Mapbox typical extension or C library, and that actually does vector tiles in a very clever way. So at really low zoom levels, you drop a lot of the features and you keep only those that basically represent the structure of your data. And then as you zoom in further and further, you have tiles with more and more data points. And that actually makes a very, very nice experience. I'll be visualizing 15 million points tomorrow, and then just go like this. So you don't have to store it. You don't have it on your laptop, you just basically store it online.
Okay.
You just pass the URL. So there is a lot of stuff going in that direction.
Great. Yeah, definitely a talk to watch. Any other comment, question?
So the BR package to connect to, like now we make a one file, basically you put the whole ISA2, they have, I don't know, thousands of files. Now you put it in a one file basically, right? And you put it on S3. And now if people know where it is, then they can connect and subset and do things. But how do you do it with R?
Yeah, with R, I have a example here. So I'm just using the arrow our package. In the hackathon I provided, but the problem, yeah, it's actually possible as we heard, but the way that I did, it's not the most clever, but I just downloaded the file and I'm reading it. But if you compile this package, the arrow package with support to the S3 access, and it takes time, you can actually read directly to the S3 without downloading the file.
Works really well. You just connect to the S3 bucket, and then you can list everything that is in there, and then you can do your dplyr queries. It's basically like using dplyr to read from an SQL database. It's the same thing. You just connect to the file, and then you do your dplyr queries, group-by select, or whatever. A few of them are not supported yet. And then at the end, you go collect, and then it's.
Is there a tutorial somewhere?
Yeah, there is. Danielle Navarro is the person to search on Google, and she has 2 or 3 very good tutorials on using arrow command.
I remember that Dewey Ellington also wrote some nice blog posts.
Yes.
Yeah, send us a URL. I couldn't find Daniel Navarro.
Yeah, I'll take him out and put him on the house, please.
Great. Okay. Any other comments?
I have maybe more general question. Why do we need both GeoParquet and GeoRL? Because right now we heard that GeoParquet will use GeoRL in the future. So why do we need both?
Oh,
As I said, Parquet is basically for long-term storage on disk, and Arrow is optimized for in-memory.
Yeah, but we heard also that GeoRL will be used by GeoParquet in the future.
Yeah, but GeoArrow is a memory layer. It's a memory file format. And if you want to save the disk in the file format, which for that, this is Parquet.
So I assume that in future most users will use GeoArrow, and if you want to save something for like longer term, you will just need to decide that maybe that's the time for you.
No, what you will do is that you will say GeoParquet. You will use Arrow as a memory layer.
Also the other way around. Most people will use
It
GeoParquet.
will be still the file format on the list will be Parquet,
Yeah, but
but memory is the middle.
okay, so that makes sense.
okay. More questions? Comments?
Daniel Navarro has a blog post called Notes from a Data Witch.
Yes.
And he has a blog post on generative art in art. How to make beautiful art in art.
Yes, there's a whole movement. Welcome to Twitter.
Okay, so I think we can close the session.
Yes.
Yeah, thank you. It was a nice discussion.
It was nice to see the theory and application. And it's very exciting, this functionality. It's great, it's open source. But there's still lots of things missing, especially visualization. Like it's horrible to do data science and you don't see what you're doing, right? I mean, you have to subset randomly and then write to your package or something, then open and then again and again. So,
There's also 2 Medium posts, I think, by a person called Carl Barron on how to visualize straight from Parquet into MapGL or something, TechGL, using Python. So that is also possible, but it's not optimized because the geo encoding is just not optimal.
Okay,
And
yeah,
then
please send it on your MetaMask.
another way of working with data of this size, trying to visualize them as a data shader, which is parallelized on the fly engine with rasterizing the vector. So instead of showing all the polygons, you get the rasterized version, like if you were doing the pyramids on top of the geodit. So, and whenever you zoom out, it does the query and it rasterizes again what we like to see. And that is a way, at least in Python, where all of you was from Anaconda, how to look into a large data set.
How it called?
It's called data shader.
Okay.
It's
Nice.
not existing now.
Okay, we can stop. Yeah, we can stop with the recording. So please stop.